Good evening, everybody. Can you guys hear me? No. Test. There we go. All right, good evening, everybody. I'm Elisha Byron. And here's the team. We are the Citadel Express. Woo. Last but certainly not least. All right, so why are we here today? So down in West Ashley, there is a model train club that's been around in the Citadel Mall since 2015. They have a large ASO scale layout that they operate on every day of the week, and they have a lot of older systems, and we went in and upgraded and implemented an automatic train control system to protect their equipment. And overall, the goal was to enhance realism of the layout and increase the educational value for those who visit. So outline of today's presentation, we're going to go through an introduction of what we did, like we just talked about. We're going to go over the problems, go over our objectives and how we solve those problems. We're going to go over a breakdown of the modules, our implementation results, overview of the budget, evaluation, of course, conclusion, and we'll follow up with some questions. I apologize ahead of time. We do have a couple short videos. If the volume blows your ears out, I'm sorry. So the overall problem statement is that, like I briefly mentioned before, the train control system that is currently there, sure, it's modern, it uses phone technology, Wi-Fi, but the actual protection piece that prevents trains from running into each other or braking is not in place. So what we did is we went in and installed various modules and components that allow trains to be automatically stopped and monitor their condition to protect these expensive models.
So for our objectives, our main goal was obviously to design, test, and deploy this to train detector system at the Citadel Model Train Club at Citadel Mall. So we wanted to minimize the risk of collisions and derailments along the main line and have a friendly user interface. There's like over 100 members of the club, so I want to make sure it was pretty friendly and user friendly. So we want to stay within budget, which we did. We'll go over later. And so we designed the train occupancy and control system, and then we had a hot box detector, an axle counter monitor, and then we designed the microcontroller unit control module.
All right, so for our proposed solution, we broke it down to 4 modules, one module per member of the team. So for the train occupancy and control system, it was Elisha Byron. For the hot box detector, Samuel Iverson. I was in charge of the axle counter monitor. Jared Campbell was the MCU control module. All right, so breaking it down into modules.
We just did the
I think we just did objectives. So breaking down each module a little bit more, give you some more information. So I was in charge of module 2, the axle monitor. I had it co-located with the Raspberry Pi Pico with the hotbox detector since we had we didn't need that many pins for our modules. And so I used 2 sets of copper plates that we had here that would detect whenever our train car was completely derailed. It would come into contact with only one of those sets. It would complete the circuit. It would go into a comparator. The comparator op-amp would then output a higher voltage, which would be sensed by one of the pins of the Raspberry Pi Pico and send a flag over to the Raspberry Pi 3B, which would then get that flag and de-energize the track in order to prevent one of the trains from toppling over due to the misaligned train car. And it would provide an audio output stating what had happened and why the track was de-energized. That was the abnormal condition aspect, but also for me, I had to count the axles. I had to find a way to use some contacts to provide a count whenever a train would go over and get the axle count, and then after it would leave the section of track. So the module was limited to one section of track right here. Whenever the train was able to actually left that block, it would it would be detected by a current sensor, BD20 current sensor, which, okay, yeah, and then that's more of a Byron's module. But then it would also provide a normal audio readout saying that there were no defects, and also it would provide the audio message of what the actual count was.
We'll go more into our modules too in later slides, but just real quickly, I wanted to point out that this was the layout that we were working on. It's HO scale, half of the O size scale, which is next to it. And we were only working on this section of the track. It actually wraps around. We're working about, what, 40 feet worth of track-ish. So maybe a quarter of the overall size for the HO scales, maybe a third, something like that.
Work about like 100 feet of track total.
Yeah, so we were, about a third of the overall size of the track. That was our area of operation. So it was a lot. It was a large area that we were trying to monitor and make sure that safety implementations were involved. So my module was hot box detector. I had a thermal sensor that talked to the MCU, the Raspberry Pi Pico, via an I2C communication. If it detected that a locomotive was over a certain temperature threshold, which was 10 degrees, which is really just warm to the touch. For these locomotives, if they're warm to the touch, it's considered overheating. It would send a hotbox flag to the CPU, which would then play an audio warning saying, hey, we have a hotbox. And then it would also trip relays that we had connected to circuit breakers that would depower that section of track and stop the train. It would hold that stoppage until a manual reset was hit, in which then it would clear a flag and reset the circuit breakers, allowing the train to continue moving on. The reason why we did that was because what you don't want is for someone to see that it tripped, and oh, whatever, let's just keep going. And then, so we wanted to encourage manual resets to clear faults.
And so for my module was overall train detection and control. So there's two aspects. You have the input section and the output section. So to detect the trains themselves, we have two methods of detection. You have the BD20 current sensor, which is effectively just a current probe that detects the change in magnetic field generated by the current draw from each locomotive. Each locomotive draws about a quarter amp at max power. And so that draws the actual locomotive. But not all the freight cars are powered. So we need another way of detecting rolling stock as well. So we have the DT4 photodiode circuits that identify the block. There'll be future slides that kind of show the breakdown of how the blocks are defined.
So real quick, we use the Raspberry Pi 3B for our main CPU, and we connect it to a user interface onto the computer screen that you can see right there in the middle. And we use the FPGAs as multiplexers, and we'll go into that in more slides.
All right, so major changes and updates. The major changes and updates, overall, most of these changes came about due to the fact that we had a test bench here that we borrowed from the club, and then, where are you going? And we had to... we use the space bar. Okay, here we are. Oh, why? Why do you like this? All right, no one touched anything. Great. All right, so changes and updates. Overall, the biggest changes came about when we were moving our equipment from the testing phase to the implementation phase, mostly revolving around the length of track that we were dealing with. We started dealing with little electrical nuances. For example, the buttons did not end up, the original button design that we had for the actual count was not effective. Some of the train cars just were not heavy enough to press the buttons down, so that's why we used the copper flags instead. For the MCU and CPU communication, we realized the I2C just wasn't needed, and we can just count the pulses on our own. For the signal detector network, some redundant photodiode circuits were removed, and overall we are starting to see some really weird EMI features because there's hundreds of feet of cabling for all the I/O involved here to going across the 40, 50-foot section of cable. So we started to see, because of the various power supplies, not just for our modules, but for the tracks themselves, we're starting to see a little bit of interference. So a lot of installation of pull-up, pull-down resistors were required in addition to the original design. So, kind of breaking down my module a little more, here's a quick video of a train tripping a set of signals. If you see those green ones, they'll throw down to red. That's an example of a train entering a new block and showing the train behind it that, hey, don't go past this red light. you're wrong. So overall, for the train occupancy control system, we have 10 photodiode circuits and 3 BD20 circuits that break down the blocks. Those modules on the bottom right are signal control boards and interlock control modules, which drive the signal boards and also detect the position of switches. So breaking down my system a little bit more, so the protection equipment that the signals talk to allow for positive train control and that their modules talk to are driven through a set of 3 Songo relays that ultimately are driven to 3 H-bridge circuit breakers that will trip a certain section of track based off of the alarming condition. So last part of my module is just an overall mapping of what the signals look like. So there's ultimately, a bunch of different ways to come in this section of track, a bunch of different ways to come in the middle, and then a bunch of ways to leave. So we need signals at every aspect so trains can stop and not run into each other. And next is Sam.
I'll make it quick. So we already briefly covered a lot of this, so I won't stay on too much. The MCU was our Raspberry Pi. That was kind of the processor for synchronized modules. Now I was also using the thermal sensor, D6T1A. What I was using. Here's a quick little schematic. We have the sensor, which reads the train. We're dragging a simulated overheating source as a pill bottle that we popped in the microwave for 30 seconds. That was our our overheating train. And then here's a quick video to demonstrate. That's our hot box. Detects, is detected, trips, breakers go off, which stop the train, and it holds that position until a manual reset is hit. The idea behind that is, again, that you would physically remove and inspect the overheating element.
All right, so for my module again, one thing that I did not talk about previously was the fact that I needed to provide the 3.3 and the minus 3.3 volts in order to power the comparator op amp. So I needed to find a way to bring down the 12 volt bus that was provided by the client. So I used 2 buck converters to bring that down to the 3.3 and the minus 3.3, and then I used that for several other things, just like the, so this is for the axle counter. So the 3.3 bus went across this so that when the wheel would go here, it would actually complete the circuit and then bring a logic high to one of the pins.
It's just a quick MCU pinout and schematic. We can blow past that.
So real quick, since we're out of time. Again, I use the Raspberry Pi 3B and use the CMI-7 for the demultiplexers to not only be able to change the signals whenever the train goes by, but also manually change them. And then here's an example of my user interface on the screen. So we can set the signal, reset the signal, and then the reset is to reset the Raspberry Pi Pico for their modules. And there's a quick, yes, this is a quick pinout. We kind of built like a bomb under the table. And our budget.
Yeah, I'll talk about the budget real quick since we're out of time. So overall, most of our equipment, we were able to requisition from within our budget of $1,000, spent $830. Dr. Hain was so gracious to let us use some of his FPGA modules, which greatly helped us out a lot, and obviously Mr. Nat and our 3Bs that we kept frying. So overall, how we're evaluated on this, we were successfully able to detect faults in the system, track the location of trains, and give audio readouts for locations, and we successfully remained under budget. So in conclusion, our achievements, we increased the realism of the club and educational value at the Charleston Area Model Railroad Club through implementing an automatic train control system, increased safety of people's models by having automatic fault detection and trip protection. Again, we remain under budget. And for future work, we're going to, again, since it looks like we built a bomb under there, I'm going to be attaching wire harnesses and more deeply organized equipment. I'm a member of the club and I have a key, so I can work on this whenever I want. After I graduate, if there's any upgrades that are required or that they want to expand, I'm going to go do it for them. And then, of course, setting up the system for future expansion. Thanks. Yes, Dr. Ivan.
So you said that CPU and MCU are communicating not over I2C.
Yeah, so actually,
So what is it communicating on?
we're just sending digital signals and pulses. The idea was originally to have I2C, but I had a hard time implementing I2C originally when I was, the thermal sensor communicates with the MCU via an I2C communication protocol. I had a very hard time getting that to work. And so due to time constraints, we kind of had a thing that worked. So we're like, let's just keep it working and not get lost in the details. So that's, I would have liked to get an I2C communication.
So what is it working on right now? What protocol is it working on right now?
It's just monitoring pins. So
That's
we're just sending flags and pulses.
Okay.
So we're sending
There's
pulse.
like parallel communication going on.
Yeah, exactly.
We knew what was coming from you.
No, this is actually, I don't think everybody appreciated from what you say what the FPGAs are doing here. How many I/O pins are there on the Pi, and how many different signals are you actually controlling?
Yes, so each FPGA was implemented as a 32-to-1 demultiplexer, and then the other one was implemented as a 32 or 1-to-32 multiplexer. So there are 19 inputs, various detectors and switches, and then there are 31 signal outputs to change the lights on the signals. So that is the majority of what they're being used for. The majority of our pin space was used by those guys. There's a lot of I/O.
We almost use like all 40 pins on the Raspberry Pi B. So.
Yeah, and about 300 feet of cable underneath that table. Not fun.
Yes, sir.
Doctor,
What has the reaction been from the other members of the Model Train Club?
so when we ran the hotbox detector through and got the audio readout, we got a round of applause from the entire membership that were there.
They're pretty static. Everything closely resembles real train systems and signaling, and they're all about that. So they were very, very excited when we had actual, like, as close to real as we could audio readouts for faults and for non-fault conditions. They were pretty excited about that.
Yeah, I'm sorry the sound didn't work. I was supposed to play it for you, but too bad. Sir.
So you talked about the technical skills, right? What about the non-technical skills? What non-technical skills did you learn from this entire project experience?
So non-technical skills, just material, so just project
One second,
management.
That question belongs to like each team member. So what
I think one of the big things was time management. We definitely didn't realize, like we originally were going to do like almost the entire outlay of the HO scale train model, so that's obviously a lot more than the 40 feet that we did. So taking that down and only doing one spot for the hot box and one spot for the axle monitor was a big difference. And same thing with connecting the CPU to the other modules.
I'll also say there were some gaps in experience that led us to miscalculate how long certain things would take. So again, going back to the I2C, I thought 2 days tops for me to figure that out. It took the better part of a week and a lot of begging and pleading with professors to help me figure it out. So I mean, so a lot of the time management stuff, like they were saying.
One last thing, I would say communication, just communication between the team members, because we were really tracking where we were with the module, but not necessarily where our team members were. So maybe there were times where maybe we had a little bit more time that we could have assisted other team members in troubleshooting or in brainstorming, right, that we could have used throughout the project.
you guys had fun?
Yes.
Yeah.
A couple gray hairs, but that's it.